welcome on board. This is Design the Engineering Process, a channel where we give a walkthrough on process engineering operations and design. Let's dive in. Engineers in the rough, we have a design mission on hand. Your mission, should you choose to accept it, simulate the production of ammonia through Haber-Bosch process using hydrogen and nitrogen as feedstock. The process of using hydrogen and nitrogen to produce ammonia is called ammonia synthesis. Take note. Conditions. Firstly, our feed condition. We're having hydrogen gas at a mole fraction of 100, which is equivalent to 1 in Aspen HYSYS for stream creation. And similarly, for the other stream, our nitrogen stream, it's also completely 100% mole fraction. Feed conditions, our hydrogen gas 30 bar 25 Celsius with a flow rate of 150 kilomole per hour. Nitrogen gas 30 bar 25 Celsius with a feed ratio of 3 to 1. That's our hydrogen ratio to our nitrogen ratio. Process setup. Both feeds shall be compressed to 200 bar. Hydrogen and nitrogen streams shall be mixed before entering the reactor. The reactor setup. Reactor type, conversion reactor. Reactor pressure 200 bar. Reactor temperature 450 Celsius. Reactor pressure drop 2 bar with a single pass conversion rate of 20% nitrogen conversion. Reaction stoichiometric coefficient for ammonia synthesis reaction is given below alongside the ammonia synthesis reaction itself. Product yield target ammonia product. We're expecting a purity of 95% mole fraction for our ammonia in our ammonia product stream. Then for our production rate, that's our quantity, we're expecting a flow rate of 20 and more kilomole per hour. For our recycle, we're going to be doing some recycling here, similar to what we did in our previous content for our SMR reaction. We're going to be doing a bit of a recycling. Unreacted hydrogen gas and nitrogen gas may be recycled to the feed reactor. That's a process of, a process of converting the unreacted products to yield more ammonia products, finished ammonia products. With this, we are set to move on to the simulation environment. Currently on the modeling and simulating environment. For those of you who do not know how we got here, as we always say, you're probably in the right dimension at the wrong time. So make sure you watch our previous content to know how we got here. As always, the first step, we create our streams. And for today, our food package of the day will be PRSV, not a very versatile and regular Mr. Peng Robinson. This is his elder brother. The PRSV stands for Peng Robinson's Trigic Vera. It's more practical for our particular simulation today. So first stream, this would be our nitrogen stream 100%. 100% nitrogen with a temperature of 25 Celsius and 30 bar. Known flow rate. Our flow rate for the nitrogen was 100 and, well, actually our flow rate for the nitrogen was not given, but what we were given was a feed ratio, hydrogen to nitrogen ratio, 3 to 1. So if our flow rate for hydrogen is 150, then our nitrogen flow rate will be 1/3 of the total flow rate of our hydrogen, which is 150 divided by 3, which gives us 50 kilomole per hour. So our nitrogen flow rate will be 50 kilomole per hour. And we have successfully created our nitrogen stream. Let's call this N2. Great. Right, our second stream, which is our hydrogen gas stream, a temperature of 25 Celsius. Do take notes, my pressure is reading kPa instead of bar, so need to correct that. Not that it's anything wrong to use the kPa. Well, I'm just more conversant with some particular units, and bar is one of them. So I will be turning this 30 bar to a rate of 150 kilomole per hour, kilogram mole per hour. And for our hydrogen, 100% hydrogen, we have successfully created our stream also. As you can see, it's in gas, the gas phase, which is what we need. And let's just come back here and temperature bar, 30 bar. Good. With this, we have created our feed, our feedstocks. So next up, we have our process setup, which tells us that both feeds shall be compressed to 200 bar. So we introduce our compressor. Good. Introduce our compressor. Plug in our nitrogen. Compressor requires an energy label, ecomp. We call this our compressed nitrogen. And we require it to be at a pressure of 200 bar. We could specify here, or we could specify the change in pressure, delta P, where 30 bar we require a change of pressure, positive change in pressure of 170 bar. We specify that, and we're at 200 bar at a temperature of 304.3. Right, that's it for our compressed nitrogen. So we do the same thing for our hydrogen. Hydrogen plugin ecomp to energy label, compressed hydrogen. Also, also going for 200 bar, change in pressure 170, and our worksheet puts us 200. Temperature 315.9 Celsius, 304.3 Celsius. So from our process setup, hydrogen and nitrogen streams shall be mixed before entering the reactor. Take note, our reactor temperature is 450 Celsius, and we're currently at 300 Celsius for both of our streams. That means we will be doing some extra heating. We need to be doing some extra heating before going into our reactor. So we we could just let's mix this. Let's mix, and then we can do our heating to this mixed feed. Right. Oh god, I mixed that up. This did this much better. Right, so let's see what our temperature looks like. 311 Celsius, we need to be at 450 Celsius, so we need to do some heating. But I believe this is where we can do our heat recovery and optimization. We can recover heat basically. We can recycle heat. If you watched our previous content, we tried to do this, but unfortunately we could not because the outlet stream from our blah 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 did not have enough energy for blah 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 blah. For those of you who were there, well, basically we're going to see what that looks like. Hopefully, in this particular content, it's going to work. So, not a heat exchanger. Sorry, heat exchanger. Good. So we we plug our feed, let it go through the tube. Let's call this tube out. And then tube out. And actually, we're supposed to experience some pressure drop in our heat exchanger around 0.1 bar to 1 bar. Let's cap that at let's cap the pressure drop at 1 bar. So what we're going to do is just going to have compression our compression pressure outlet, our pressure to be 201 bar. Let's say 171. That puts us at 201 bar. Good. The same thing for our nitrogen. Design parameters 171 bar. So it's specified. Okay. 171 bar. This is serious. Specified, you see. What do we have going on? Oh my days. Exactly is our issue right now. Let's check this out. 170 bar. Well, that's a shocker. Good. Aspen HYSYS and Aspen HYSYS things sometimes. So 201 bar. That's very much good. And we experience a pressure drop. Let's specify the pressure drop to be 0.1 or 1 bar actually for our shell side and 1 bar for our tube side. And I think right. So temperature 450 according to our write up 450. That's our reactor temperature. So good. But take note, the heat exchanger has not completely been solved. We just we just call this manipulation a way of manipulating it initially for the meantime before we solve it. We're going to just adjourn the heat exchanger conversion till we get the product for the shell side. Now, our reactor. Remember, we're using a conversion reactor, and that's our conversion reactor for our Haber-Bosch process, ammonia synthesis. But remember, a reactor does not work without reactions. So we have to specify our reactions. And to do that, we're going to select this and we're going to attach a fluid package to this. Attach advance. Right. So add our reaction, conversion reaction, reactant source HYSYS, of course. Let's call this ammonia synthesis. This is, and we double click, we go in, we add our components for the reaction nitrogen, our product which is ammonia, and let's see. I think we are good to go. So our base component, which we forgot to mention, our base component in this simulation would be nitrogen. Unfortunately, it's not popping up. We specify our stoichiometric coefficients. That we haven't specified that. Hydrogen -3, nitrogen -1. So specify that -1, -3, and this would be 2. Good. Balance 0. Base component. Good. CO represents CO is a parameter used to find our conversion reactor. But in this case, we're just going to specify CO and it gives us our conversion rate, which we already have. CO is used to make up that. And in this case, from our from our write-ups, we have a single pass conversion rate to be 20%. And the reason for this is that prior to what we might have been experiencing in previous simulations where we have conversion rates of 80%, 90% in our reactor, for the Haber-Bosch process, it's slightly different. The ammonia synthesis conversion rate is slightly lower. Ammonia production rate is lower. The reason for that is that this is you can see this double-sided arrow, two arrows rather. One is going forward and the other one is going backwards. It's a reversible reaction, equilibrium reaction. So in as much as we combine nitrogen and hydrogen to produce ammonia, we can decompose ammonia itself to create to create our to break down and collect our hydrogen and nitrogen gas. The problem with the ammonia synthesis process is simultaneously as you're creating ammonia, you're producing ammonia. Simultaneously, on another side, you're also decomposing the ammonia. It's a reversible reaction which happens simultaneously. Hence, you have to balance the whole process, though you might not be able to see the whole process kinetics in Aspen HYSYS, but chemically, if you check it chemically, the process happens simultaneously. So this affects the conversion rate. And that's why usually for the Haber-Bosch ammonia synthesis process, it's usually more than a single process, a single pass process where you just send it in and with one reaction or one reactor, you've created sufficient ammonia. The ammonia production rate is usually lower, so you need multiple reactors or you need to keep carrying out reaction loops, recycling loops, rather you carry out recycling loops where you recycle the unreacted products which have decomposed from the ammonia synthesis. You send them back to your reactor to produce more ammonia products. So with this, we understand why our conversion rate is lower. 20% nitrogen conversion. Nitrogen is our base component, which has already been specified for us, and everything is balanced. Everything is good to go. We just add our 20% here and we are ready. So our reaction has been set. We head back to the modeling environment. So we're good to go. We plug in our product reactor inlet, which contains our mixed compressed and heated hydrogen and nitrogen gas. We're going to call this let's just call this tops, bottoms. Right, and then we specify single pass, yes, and we specify our reaction, and we have successfully converged the reactor. Now the question is, have we produced ammonia? As you can see, at the top we have a flow rate of 180. At the bottom we have 0. 200 went in, and we have 180 here. Take note of the temperature, 450 Celsius. But after the reaction, it generates heat. So we have an increase in our heat. And our pressure drop, which we failed to specify. What was our pressure drop again? 2 bar. So we failed to specify that. We can just go back. Pressure drop 2 bar. And you can see it reflects 200 bar inlet pressure, 198. And you can see how it affects the pressure. Well, Aspen HYSYS, we might need to carry out that process again. Let's just drop a new reactor. Conversion reactor. Where are you? Tubing. Tops. Bottoms. single pass, two bar, reaction set. Right. You can see the temperature, 633.1, 198. So that tells us we're good to go. Aspen HYSYS sometimes can be very funny. The moment it reads an output value, it writes it into the memory, and sometimes even if you change the parameters, it refuses to change the previous value to the new value. So you might just need to delete the equipment and drop a new one and do the process again. We're supposed to be checking our tops. This is where we have our ammonia and most likely unreacted hydrogen and nitrogen gases. Composition, as you can see, ammonia. We basically produce only 11% ammonia. We still have 66% unreacted hydrogen and 22% unreacted nitrogen. So does this satisfy our targets for ammonia yield production 20? Nope, it doesn't. Well, actually, we can't see unless we do the math. So let's just quickly do the math. Firstly, this is our mole fraction, remember, not our molar flow rate. So we need to do the math. 0.1111, which is 11%, times our total flow rate, which is 180. That gives us 19.998 kilogram mole per hour. So approximately, yes, we're there, but why not? Let's recycle the unreacted and see if we can produce more unreacted ammonia. So technically, yes, we're there. But also take note. Also, we expect a purity of 95% mole fraction ammonia. So we have to purify this ammonia. To do that, we're basically separating the ammonia from the unreacted gases. And luckily, it's easier. It's easily done here. In this particular case, we just condense. Now, showtime for the heat recycling magic that we have been talking about. Take note of our temperature here. It's 633.1 Celsius, our product, and this is 312. So we definitely have temperature, so heat energy to a very large extent, which we can feed this particular stream, even though the flow rate is slightly higher, but we still have enough change in temperature at least to push it higher to a new degree. So what we're going to do, we're going to plug in this this ammonia and unreacted gas stream. This is going to be our shell side, which supplies it heat energy. It's all going to aid our condensation process as that particular stream loses its heat. It does well for us. We bring about condensation and we can just drop a separator to separate the ammonia from the unreacted gases. So we're going to call this shell out. Shell out. And let's see what it looks like. Lost lost about lost 150 plus Celsius. And it works in our favor, very much works in our favor. No temperature crossing. It pushed the temperature to where we need it to be. And voila. Instead of having a heater wasting heat energy and it brings about costs, increment in costs, you can just recycle heat like this and you're good to go. So heat successfully recycled. And we're going to be doing some condensation here still, most likely. Yes, we're still at the gas state. So we're going to do some condensation to bring about liquids formation, and then we can just simply separate. Come on, HYSYS. So shell out, equaler 1, outlets condensed. Condensed. Did we call this condensed? It's not fully condensed, but let's just say condensed stream. Right, change in pressure. What kind of change in pressure do we want to give it? Unknown change in pressure. Let's just say 0.5 bar. Temperature. What temperature do you think we should be at? What temperature does nitrogen and hydrogen condense? Let's see. Let's do a research on that. Condensation or boiling point, you could say boiling point, or at what temperature? There's nitrogen and hydrogen gas condense. Bear in mind, pressure also affects this. Pressure is also a very paramount factor in this particular case. So at 1 bar, the boiling point the boiling point of hydrogen is negative 252, approximately negative 253 Celsius. For nitrogen is negative 196. So we have some pressure drop to do, temperature drop rather to do. Let's start with negative 150. See what it looks like. Okay, we drop the pressure. That's a very, very low temperature. Vapor fraction dropped. So let's introduce our separator. Separator, which is a knockout drum, basically. It's essentially a knockout drum. Let's see, condensed stream, all this gas, liquids. Right, so let's see what we have. So all our hydrogen and nitrogen, that's all we have here, and ammonia at the bottom. Yep, 100% ammonia, 100% ammonia down here. So golden question, let's see. Flow rate 20 kilogram mole per hour, approximated our 19.999. So basically what's it's telling us is that at the negative 150 with our current pressure, because it's very, very much high, we are able to completely separate them 110% effectively separate our unreacted gases from our ammonia. So let's just reduce that. Let's reduce that pressure, change in pressure. Let's say negative 100, and let's see how it affects us here. 99.9, 19.998. We still have slight traces, slightly. The traces are slight, 99% purity and 19.98. I think let's realistically leave it at negative 150, or let's say negative 120. Yeah, that does the job. It approximates our flow rate to 20 kilogram mole per hour. And at the top here, let's see, are we completely left with unreacted gases? Yes, we are. So this particular stream unreacted gases, let's properly name this unreacted gas, and the bottom, we will call the bottom our ammonia. NH3. Good. So we recycle this to our reactor feed. Now, where do we plug this? Where exactly do we plug this? Let's do it this way. Well, first, you actually need a recycle 3. We call this 3, and we drop that. We send this in unreacted gases, outlets, re this re out, recycle out, and it's basically the same thing. Nothing changes in our parameters, as you can see. It's just that we have to include the recycle loop to tell Aspen HYSYS, our very, very smart Aspen HYSYS, sarcastically speaking, a very, very smart Aspen HYSYS, that we have a recycling stream for you. Please collect it by all means. And you just pop this here, out. Ooh, yeah, messes with things that much. So usually recycling, we might not be able to recycle everything sometimes. Let's break this. Usually we split. I was trying to be too greedy, sending everything. Usually split. Let's just make sure yep, our products are still there at the temperature of, yep, everything is intact. So let's do a split firstly. Unreacted gases. Split it to, let's call this zero, let's say half. And another stream would be, what would be second half? Let's say second one, second half. All right, specifying the split ratio 0.5. Let's equally split it 0.5. So let's see, what does that make up? Does that make up 160? 160. So that would be 80/80. Now let's introduce our recycling loop. We half. Right. We out. Good. Now do not disappoint us. Let's go. Plug in. Voila. Mm-hmm. We have a temperature cross. Wow. This is so good. Basically, let's reduce that. Let's reduce that. Right, 0.2 at least. 0.2. 0.2 at least. Second 0.2 at least. Even 0.2. Mm-hmm. Alright, 0.1 at least. Aha, that works. Recycling 0.1. And you can see we have 21.74. We increased our yield. Let's just make sure everything's alright. Yep. Our yield increased from like 19.99999, approximately 20 kilogram more per hour, to 21.7. So that works in our favor. Basically, recycling work. The split, you have to make sure the split does not tip the balance of the convergence in your process. It's an issue that keeps recurring regarding recycling, and I'm pretty much sure it's a real world engineering issue too. So you have to make sure your recycling rates does not tip the balance of the process also. So let's just be a little curious. Let's push this to 0.15. Is that acceptable? Yep. What does our yield look like? Good, 22.2%. Let's push that. Let's push it 0.18, 23, 23. Temperature cross. Let's just push that a little back. Wow, congratulations. We messed up everything up. Aspen HYSYS 0.1 and then doesn't even work. So what did we mess up? Come on, big boy. hmm You basically got the whole concept of it. We've messed up everything and we need to set up the reactor. But you could see how everything worked out. So, can we say that we have successfully carried out our mission? I think to a very large extent, yes, up until the final point where we messed up everything. Basically, that's it for ammonia synthesis, and you could see how we were able to reach a purity of 100% for ammonia, which is great, and a quantity of 23 point something something kilogram mole per hour, which satisfies our design. So, ladies and gentlemen, as always, if you followed us down this far, please make sure to like, subscribe, and click on that notification icon. Thank you very much. See you in our next content.